We started talking about different helices. We have helix of n equals to 4, n equals to 3, n equals to 2 is not really a helix anymore. And then you have n equals to minus 3, then it's going to be on a left-handed helix instead of a right-handed helix. Now, n here, okay, so all the little n here, they represent the number of polypeptide residues per turn of a helix. And what turn means is when you start from this amino acid residue, the next time when you get to the same position here, that's essentially one turn. Okay, so n equals to 4, meaning you have 4 amino acid residue to reach the same location from the initial amino acid residue. Okay, all right. So alpha helix. Remember we said that secondary structures for proteins, the most important ones are alpha helix and beta sheets. Now, alpha helix, in this case, the hydrogen bonds are formed between the amino hydrogen and the oxygen of the carbonyl. Okay, so it is with these hydrogen bonds that pair between the carbonyl oxygen and the amino hydrogen such that you form a very stable structure that looks like a helix. Okay, and this is the helix shown on the right here. Okay, so a general structure. And as you can see, every time you have, this is the amino group, that's a hydrogen. Hydrogen is going to pair with carbonyl of another amino acid down the road. What you also notice is that the R group of each residue point out, meaning away from the helix. So you have R group pointing that way, R group pointing this way, R group pointing that way, and then for the ones that face towards the board, essentially you have, this is R group and it's sort of coming out at you, and then if it's pointing away, for example, this particular carbon, the R group is going to point away from you. Okay, so essentially you can think of alpha helix as a cylindrical shape, and the R group sort of radiates out from the axis of your helix. Okay, so R group sort of points out. Right, that will be important towards the end of this class when we talk about how you have different phases. Okay, phase as in like face. Okay, different phases that will have similar hydrophilicity or hydrophobicity. Now, another thing to know about helix or alpha helixes is that most helices, they form as a macrodipole. Okay, what that means is that there's going to be a dipole moment for each of these hydrogen bond align. Okay, so as the hydrogen bonds align, you have, for example, here, this is the oxygen. Down here, this is more of the hydrogen. Okay, so you still have a dipole moment for the entire helical structure, because as you can see, towards the top, you have the carbonyl. Down the bottom, you have the hydrogen. Okay, and then as a result, usually we say then the N-terminus is usually partial positive, because N-terminus has the amino hydrogen, and then the C-terminus is going to be partial negative because the C-terminus has the acid group. Okay, and the acid group has that C double bond O. Okay, so that's going to be partial negative. Here is going to be partial positive. Okay, so this guy is going to be partial positive. All right, so if you were to take a top-down view on the alpha helix, this is exactly what you'll see. As you can see how it sort of rotates and the R group sort of spins around the helix. Now, the hydrogen bond forming pattern, okay, the hydrogen bonds are formed between residue I and I plus 4. Okay, so essentially you have residue 1, okay, and then you have 2, 3, 4, and 5. So you actually form like that. Okay, so it's I and then I plus 4. Okay, so if you want to form a hydrogen bond, then you go from the first amino acid amino acid number 1 is going to form hydrogen bond with amino acid number 5, so I plus 4, okay? For each turn, unlike an ideal helix where you have integer numbers, alpha helix does not have an integer number for the number of residues that it has per turn. Turns out it has about 3.6 residues per helical turn. Okay, and I'll show you essentially what that means. Okay? But first, to have a repeat, okay, an exact repeat, then you will have 18 residues are needed because for every turn you make for the helix, okay, it's 3.6 residues, right? And you want to have an exact repeat meaning that the amino acid at this position, the next time you have an amino acid at the exact location, but higher up, it's going to have 18 residues away. Okay, not 3.6. 3.6 sort of means like this. You first start with this amino acid, okay, and then you have helix, right? And then the next time it comes back to this. So per turn, let's say it's like this, okay? What you see is that the amino acids, they're not at the exact location, okay? You see how this and this is not at the exact location. So that's why it's per turn, okay? So this is one turn from here to here, right? You have 3.6 because you have 0.6 of an amino acid that will base pair with the number 1 amino acid. Okay, I'll show you a better picture than this. All right, but just have a repeat essentially means that you have to go again this, so another 3.6 and another, essentially until you reach a position that is identical to this guy. This amino acid, 18 residues later, you end up at the exact location. Okay, the exact location. That's what it means. Okay? You have 18 residues for the 18th residue to be at the same location as the initial one. Okay? So in order to repeat the next, in order to get to the same location, you have to have 5 turns, essentially. Sometimes alpha helix can also be referred to as a 3.613 helix, okay? And what this represents is it has 3.6 residues per turn with a 13-member ring joined by the hydrogen bond, okay? So if you look at this, we say this is, start with this guy's 1, and then we have 2, 3, 4, 5, 6, 7, 8, 9, 10, coming out 11, going to here 12, 13, okay? And the number 13 molecule, well not molecule, atom, is going to have the hydrogen bonding with the number 1 atom, okay? So together they form a sort of like a circular structure, okay? Because 1 and 13, they have hydrogen bonding, right? So together they form a 13-member ring, okay? So that's why it's called 3.613, right? So this is alpha helix. So alpha helix is one of the most common secondary structures that you'll see in proteins. Now, I'm going to show you a couple others, one of them being the 310 helix. Now, the 310 helix is observed in some proteins, but not as common as the alpha helix. Now, the 310 helix has exactly 3 residues per turn, okay? So if you look from the top-down view, it's exactly, you see a little triangle there. And because it has 3 residues per turn, if you want to make the ring structure thing, you see how it's a 10-member ring where you start again from your, this is hydrogen, right? So the hydrogen donor, hydrogen being number 1, okay? And then 2, 3, 4, 5, 6, 7, 8, 9. And then 10 is the oxygen, okay? And then they bind. Okay? So 310 helix is another type of helix, and it's not found as many as your alpha helix. Now, what you notice from the top-down view is that your R groups are sort of stacked together in the 3 locations, right? One here, one here, one here, because you have exactly 3 residues per turn, so that to get to the identical position of an amino acid, you only need to have 3 residues. As opposed to alpha helix, you need to have 18 residues. To repeat the same location for alpha helix, it's 18 residues. For the 310 helix, it's just 3 residues. Okay? So as a result, your R groups are going to be stacked at 3 positions. So essentially, it's like the 3 corners of a triangle. So immediately, you can think now, if you have bulky R groups, this is not going to be a good thing because the bulky things tend to hit each other. Okay? Right? So again, alpha helix, you see how it's not, you don't repeat. So in order to repeat, for example, this guy, you need to have 18 residues down the row to repeat exactly this location. Okay? To repeat that location, you need to have 18 residues. That means that the R groups are more spaced out. Okay? You have more angles difference between the R groups. Okay? So it's more spaced out. So usually it's more stable. All right? Another helix is the pi helix. It's not exactly a helix, really. Sometimes we just call it the alpha bulge. Okay? So it's sort of a mutated alpha helix by inserting 1 extra residue, right? Such that you generate this pi helix. Now, pi helix turns out to be quite widespread. Okay? It actually causes a little kink to your alpha helix. Alpha helix is a cylindrical shape. It's like a rod. But if you have a pi helix in the middle, you sort of bend that rod. Okay? So the occurrence of pi helix is likely due to a mutation resulting in insertion of an amino acid into an alpha helix. Okay? Thus causing a little bulge. So essentially, you have 2 polypeptides here. This polypeptide gives you a very beautiful alpha helix. Right? Now, all of a sudden, you insert a glycine, okay? And it sort of destroys your alpha helix. And then you generate a local structure called pi helix. Now, pi helix, essentially, what it does is instead of doing a I to I plus 4 hydrogen bonding, now with pi helix, you do a I and I plus 5 hydrogen bonding. So essentially, you see how this is the width of your alpha helix. And with pi helix, you see how it becomes wider. Okay? So it sort of causes your helix to sort of bend because it's wider, and then your helix is going to be twisted towards the sides. Okay? So that is pi helix. Now, so if we sum up the 3 different helical structures that we see in proteins, what you have is you have a small binding, meaning short repeat, that is the 310. Okay? And this guy goes from I and I plus 3. If it's alpha helix, then you go from this guy's residue I, and then with alpha helix is I plus 4. With pi helix, it's going to be I and I plus 5. Okay, so essentially pi helix, you just moved the hydrogen from I plus 5. Yeah, from I plus 4 to I plus 5. Okay? Does that make sense? So this is the number 1 secondary structures that you see a lot in proteins, alpha helix and the other helical structures. And please understand how they fall, okay, and how they're stable. Now, I want you guys to know the relative difference between 310 and alpha helix, okay, especially how the R groups are oriented. You have this other weird looking helix called polyproline, or a lot of times we call it also polypeptide 2 helix. Okay, this guy is really weird because it's not exactly a helical structure that's stabilized by the hydrogen bond between the carbonyl and the amino group. Okay, it's not, right? And essentially what happens is every time you have a polypeptide 2 helix, it contains approximately 30% proline residues. So when you have a sequence that's going to be rich in prolines, usually you're going to see some polyproline helix, which hence that's where they got the name from, polyproline, okay, because it has a lot of prolines. Okay? Sometimes if you have a lot of glycines, so polyglycines can also adopt this particular conformation. Now, instead of a right-handed helix like the other guys, this guy is a left-handed helix twist. Okay? So the twist is indicated by the curvy gray arrow, so this. Okay, so it's a left-handed helix instead of a right-handed helix. And this structure, like I said, does not have hydrogen bonding between the main chain of the polypeptide. Okay, and the reason why this forms is because for the most part, you got proline, this awkward amino acid that has this awkward bond angle that helps it to form this particular structure. Okay, now you're definitely gonna ask me, how is this structure used? Okay, I don't know that from the top of my head. You can go look it up, see if you can find any uses in this particular structure. But what I can tell you right now is that secondary structures does not, most times, it does not have a exact function. Okay, it just provides a backbone to the structure. Okay, to the structure of the enzyme, and then it's the structure of the enzyme. Okay, depending on what R groups you guys have, then it defines what the function of the enzyme is. Okay, so secondary structures, they just provide a backbone for the structure to occur. Okay, just so that you know what this thing is. Alpha helix 跟 beta sheet， 大家看到 beta sheet 哦，那它其实它只是一个有点像是一个 structure 的 backbone 我们说有点像是它的一个基本结构。那 depending on 你的 R group 的不同，它会形成不一样的 structure。Okay? 所以我们所以在讲这些 helix， 它只是一个方法，让你的 amino acid 有一个可能直筒状的形状。And then depending on 你不同的 R group， okay, 在不同的位置上，它可能会导致你有某一边特别 hydrophobic， 那边特别 hydrophilic 之类的。Okay? 所以这个 secondary structures 呢，它不代表说它一定有一个特别的 function。Okay? 那个 function 还是 dependent on 你的 amino acid 的 sequence。Okay? 它有什么 R group？ 那这个 alpha helix 跟它隔壁的 alpha helix 有什么样子的关系 ？That determines 你的这个 function. Okay, so we can't tell the function of a protein based on secondary structures. You have to see it from tertiary structure. Okay, beta sheet, very quickly. Beta sheet, you also form beta sheet based on hydrogen bond between the amino hydrogen and the carbonyl oxygen. Same thing, okay, same thing. Now, except that instead of a helix, okay, you form a sheet-like structure where essentially you have alternating directions. For example, this one looks like that, and then the next one you flip like 180 degrees, and then you get this. Okay, and then it's just so go on and on. So if you look at the beta sheet, okay, from a side view, this is what you'll see. Hydrogen bonds sort of force them together between the main chain, and then the R group point opposite directions between the two neighboring residues. Okay, so for example, R group for this guy point down, so the neighboring residue is going to point up, and then it's going to point down. It's going to point up and then point down. Okay, so the R groups alternate. Okay, so it's kind of like a little zigzag structure. Okay, now beta sheet is the overall structure. We call that beta sheet. If you only have one of them, one linear chain, we usually call that a beta strand. Okay, and then many beta strands together generate you a beta sheet. Essentially, you have two residues per turn. Okay, now the concept of turn here is a little weird because in helix we know one turn is exactly when you start from here, go in a circle, come back to the same position. That's one turn. That's one helical turn. Now, beta sheet is different, right? Because it's not a helical structure. It's more flat, okay? So it's flat, right? So let's say you want to start from this structure and you want to regenerate this structure. So I plus 1, and then I plus 2. Okay, so it's very simple, right? So you go from, let's say, from there, right? You want to get to this structure, right? Right? I, so this guy's I, this is I plus 1. So this structure is different from this. Okay, 明显吧? Okay, 明显哈, this structure is not. So when you repeat to this guy, then it's going to be like that. Okay, so this guy is I plus 2. So this position is a rectangular, it looks that, I don't want to draw an arrow to confuse you. So this rectangular structure repeats when you are at 1 plus 2. Okay? Because I plus 1 is facing the other way. So you have per turn n is equal to 2. Right, so if you flip back to our notes, okay, you will see, remember at first we said n equal 4 is a what you may call it? It's a helix. N equals to 3 is a helix. N equals to 2 is a flat ribbon, right? So this is exactly what that is, okay? N equals to 2, okay? So 2 residues per turn. Not that you guys really care, right? All right, your strands, okay? Your beta strands can be parallel or anti-parallel, okay? What does that mean, okay? If you have an anti-parallel strand, okay, you go from, this is the N terminus to the C terminus, right, on this strand. And then the strand that does hydrogen bonding with it sort of essentially is now N to C, so it sort of comes back, okay? So they're anti-parallel. Parallel, then it's similar idea, you know, this is N to C, so it's going this way, and this guy is also N to C, going that way. Okay, so regardless of you being parallel or anti-parallel, okay, you can all have beta sheet. Okay, and then you're going to ask me, okay, so what's the difference? All right, so I'm going to tell you what's the difference, all right? All right, so the difference is shown on the slide, okay? For the anti-parallel ones, you have linear hydrogen bonds, okay? For the parallel ones, you have a slanted hydrogen bonds, okay? What's the difference, okay? Linear hydrogen bonds are stronger. Why? You're going to ask me, are you sure about that? Okay, usually it is, right? Because the forces, right, when you a while ago, that's why we actually make you guys learn physics. Okay, that makes sense. All right, so if you think about it, right, hydrogen bond, you donate the hydrogen in this direction, okay, and then you're accepting hydrogen in this direction, okay? So you have donating, accepting, okay, so you have a very good interaction right there, right? But if it's slanted in an angle like that, okay, then it becomes a little complicated because you're donating this direction. This guy is accepting in this direction, okay? So you sort of is looking for a junction between the two directions. Make sense? So you can sort of, the interaction there, you can split that into the y component and the x component, okay? So obviously, because this interaction is slanted, all right, then you know, overall, the y component is going to be smaller than that guy. So if you want to have a very tight binding, you're probably going to be looking at linear hydrogen bonds, and that's why you need an anti-parallel beta sheet. Okay? Yeah, just like that. Okay? So this is a short summary. This is a summary in terms of what are the distance measurement between the different secondary structures. You got the beta strand parallel, anti-parallel and beta strand parallel. No, both of them are 2 residues per turn, and what you see is that in terms of rise and pitch, okay, you actually have a larger rise and pitch for the anti-parallel than the parallel, okay? But obviously you see the difference is not too big. This is 0.2 angstrom. Yeah, it's pretty small. You also got alpha helix and 310 helix right there. And you also got polypeptide 2 helix right there, okay? What are these numbers very important for you guys at this stage of your career? Probably not, but I do want you to focus a little bit on sort of like the 3-dimensional size, okay? Like 310 is going to be narrower and longer, right? Just like, remember we talked about A form and B form DNA, right? One is skinnier but taller. The other one is sort of like fatter and shorter, okay? So just sort of know the general properties, but it's not like super important you memorize these numbers, okay? Now, going beyond that, actually I want to have you guys take a look at this, okay? So, turns out your alpha helices and beta sheets can be amphipathic. Do you guys remember what that means? Okay, it means that it can be both hydrophobic and hydrophilic at the same time. Okay, not exactly at the same time. Okay, it's more like you have one end that's hydrophilic, one end that's hydrophobic. Okay, so just like your fatty acids. Okay, like your SDS, that kind of stuff. All right, so your amphipathic for alpha helices and beta sheets refers to having hydrophobic face opposite to hydrophilic face. So helix, it's like a rod. Okay, it's like a cylinder, right? It's like a cylinder. Cylinder has face, like you can say this face, that face, and that face. Okay, so cylinder has different sort of faces to it, okay, because it's a three-dimensional structure. A sheet also has faces, two faces, this face and that face. Okay, so top face and bottom face, right? So because these structures can have three-dimensional faces, that sort of means that you can have different hydrophilicity or hydrophobicity to the different phases. And then that will give you a good advantage in binding and do all sorts of different things. Okay? Now, turns out your alpha helices will have R groups of similar polarity for every 3 to 4 residues. Why is that? Because remember, every time you make a helical turn, it's 3.6 amino acids, right? So if, let's say, today you have a rod, okay, you have a rod, and you want this side to be hydrophilic and this side to be hydrophobic, okay? Then let's say you have one amino acid right here that's hydrophobic. You want to make sure the next amino acid on the same phase is also hydrophobic. So it's going to be 3.6 to make a one turn, right? To make one turn. So you have every 3 to 4 amino acids in the sequence are going to share similar polarity. Then you will have an entire face, okay, the entire side of this chalk to be hydrophobic. Same idea for hydrophilic. Okay? So every 3 to 4 amino acid residues, you will have similar behavior, meaning okay, similar polarity. Right? So if you have phenylalanine, the next one is probably phenylalanine or tyrosine or whatever. Okay? Beta sheets will have R groups of similar polarity on the same side of the sheet, okay? Essentially alternating residues, right? Because we say in beta sheet, you have this R group pointing up, the neighboring R group is going to point down, and then point up, point down, point up, right? So essentially, what you have is, if this guy is I, so then the next time you have a residue pointing in the same direction is going to be I plus 2, right? Because I plus 1 is pointing in the opposite direction, okay? So based on this, okay, if you want to go home and design your protein, you can already do it, right? You can say, I want to have 4 rod bind together, okay? Let's say I want to have 4 chalk, okay? 4 chalk bind together, okay? Then as long as you make one side of it hydrophobic, okay, and then you have 4 different alpha helix, 4 of them have a hydrophobic side, then when they fold, they're going to come together, and then that form a protein, okay? Right? And then on the other side, you can have your hydrophilic, okay? And hydrophilic can do, you know, solvent and protein interface. It can do active site. It can do whatever, okay? So this sort of, does that, do you guys now have a little picture of how proteins may be assembled? Okay? Because, like I said, proteins have in the most part, alpha helix and beta sheet. Now, your alpha helix and beta sheet can have hydrophilic and hydrophobic phase. Hydrophobic ones will sort of aggregate, and then you have the hydrophilics, right? So then, very easily, you can imagine how you have different rod structures or different sheet structures that can sort of interact with each other in 3-dimensional space and then form you this big enzyme thing. All right. So one other thing I want to talk about before we move on from secondary structure is obviously turns. Okay? Like, okay, we have alpha helix and beta sheet. That's fine, you know, but then where and when does my structure stop being alpha helix and beta sheet, right? That's a good question for you. Like, I can have alpha helix, but then how come I don't just alpha helix and like alpha helix, right? I have a lot of alpha helixes in a protein. When do I stop being alpha helix? When do I stop being beta sheet? When do I turn? Okay, so proteins, obviously, you're going to have alpha helix, not like forever, right? So somehow you're going to make a turn, and then another alpha helix, and then somehow you make a turn, and then you have a beta sheet, and then somehow you have another alpha helix, right? So always you're going to be expected to make turns in your proteins, right? So then we have this thing called beta turn, right? So turns and loops are connecting sequences that link successive runs of alpha helixes and beta sheets. Okay, so these are the sequences that sort of link two different alpha helixes or beta sheets together. Okay, so they're the linking sequence, right? Beta turns are particularly common, especially for the anti-parallel beta sheet, which requires a 180 turn. Okay, so let's not look at the hydrogen bonding right here. Let's just first look at the beta turn picture. You have type 1 and type 2. Don't worry about that. All right. From here, I go this direction, right? And then this is my protein. And if I want to make an anti-parallel beta sheet, then essentially I want to have this, right? Okay? Because this is one direction, and then here is another direction. So this turn is actually a very sharp turn. Okay? So you go from here, immediately you turn, and then comes back. For a beta turn, you only have 4 residues. Okay? So residue 1's carbonyl with residue 4's amino. They are going to do your, what you may call it, hydrogen bonding. Okay? So this hydrogen bonding stabilizes this turn. Okay? Because otherwise your turn could be like floating around, right? So if you want to make a sharp turn, okay, beta turn right here is a very good choice because all you need to have is 1, 2, 3, 4, and then you make a turn. Note, glycine and proline is frequently observed in beta turns, right? Why? Because proline is restricted in the amount of bond angle that it can have for its phi and psi, right? Because proline has that weird R group that is linked to the amino group, right? The amino group of that amino acid. Okay, so proline is restricted. Glycine. Now you'll be wondering, like, how come glycine? Okay, glycine is flexible, okay, but turns out it's flexible and it's capable of making your bond. You can have a larger twist in the bond angles such that you can have a rapid turn. Okay, so in beta turns, you have type 1 and type 2. Okay, type 1 and type 2. Type 2, okay, what you notice is that the hydrogen bond is again sort of like slanted, where this one is more or less vertical, but it's minor. This is not super important. But type 2, number 3 is usually always glycine. Okay, but these are just two versions of beta turns. The difference is not important at this point, but just so that you know. So type 1 more favorable because you have a linear hydrogen bond. Type 2, residue 3 is usually always glycine. Right. One last thing that I have for you guys is called gamma turn. Okay, gamma turn. Gamma turn turns out it's even smaller. Okay, only one residue is out of the hydrogen bond sequence. So essentially you got hydrogen bonding down there and stuff like that, where all you gotta have is 3 amino acid residues, 1 amino acid residue right here, okay, and this could be whatever. Now all you gotta have is 1 proline, and then this is amino acid residue 3, okay. So 1 and 3, they have hydrogen bond, okay, and then you have 1 residue that's sort of out of the hydrogen bonding sequence. Okay? So it's out of the hydrogen bonding sequence, in this case, proline. proline with their awkward angle is sort of like make a sharp turn, and then this guy continues to go hydrogen bonding with whatever that they're hydrogen bonding with. Okay? Note that no hydrogen atom is bonded to the alpha amino group of proline. Why is that? The hydrogen that appears to be bonded to the alpha nitrogen atom is in fact bonded to the D carbon of the proline side chain. All right? So it's not bonded, the hydrogen bonding is not bonded to the alpha hydrogen. So you got beta turn, gamma turn. Okay, so these are turns in the secondary structures that would allow you to sort of have localized alpha helices fall on each other or beta sheets. Okay? All right, this is the probability of amino acid residue occurrences in secondary structures. Okay? And we got your alpha helix, your beta sheets, beta conformations, or your beta turns. Right? Now, you remember we said that for beta turns, you have a lot of proline and glycine. Right? It turns out you also have a lot of asparagine, aspartate, serine, okay? These hydrophilic amino acids, okay? For turns, you don't have as much hydrophobic ones, okay? Because turns are usually going to be exposed, right? If it's exposed or it's, sort of open to touching with the solvent, then it's not going to be hydrophobic, right? If it's hydrophobic, they like clump together. Okay, so for turns, you don't have as much hydrophobic. Okay, mostly hydrophilic, and then it's mostly proline and glycine. Now, alpha helix, okay, what you notice is that you don't have proline and glycine as much because proline and glycine are the two really awkward amino acids that sort of mess up your structure, okay? Because proline being very restricted in angle, okay? Proline is restricted in angle, and then glycine is too free with the angle, okay? Because it does not have an R group. The R group is just a hydrogen, okay? So it's too like free, right? Beta sheet then, okay? Beta sheet, beta conformation. For the most part, beta conformation, you see a lot of the hydrophobic residues, okay? For example, you see leucine, phenylalanine, tryptophan, isoleucine, valine, tyrosine, okay? Although tyrosine is not very hydrophobic, right? So beta sheet from this figure, it already shows you that a lot of times your sheets are going to fall on each other, okay? Right, so this is a very good graph that you can use to sort of look at and then see what kind of residues typically occur on where. Okay, right? And you see how like for beta sheets, you don't really have that many charged ones. Like glutamate is charged, aspartate is charged. Okay, so they don't like to be on it. All right. What else is charged? Arginine is charged, and the last one that's charged is lysine. Lysine is charged. Right? So the charged amino acids are less found on your beta sheets. Okay? All right, so that's all I have for today's presentation on secondary structures. So then, starting from our next lecture, we're going to be starting talking about tertiary structures. Now, remember what I said. I will not go into detail in tertiary structures. Why? Because tertiary structures are nothing more than a lot of secondary structures put together. And there are just way too many different types of tertiary structures, okay? And each of them have a different name. Okay? I'll show you some common names, but I will not show you, for example, how it's like specifically how it's made, like how many alpha helices or how many beta sheets. I'm not going to show you that. I'm not going to show you like exactly what they're used for because again, structures are just structures, right? The functions really depends on the interactions of the different structures, so the different 3D organization, right? Tertiary structure is nothing more than a bunch of secondary structures formed together into a weird looking shape, okay? If you're interested in protein structures, you can take a graduate level course about that. We have graduate level courses on protein structures, okay? And then we're going to talk about only a little bit about quaternary structures. Quaternary structures are nothing more than different tertiary structures come together, okay? It's very simple, okay? And then very soon we're going to dive into protein functions. We're going to start talking about, for example, the proteins that make your fingernails, the proteins that make you your collagens, your kneecap. We're going to talk about hemoglobin, myoglobin, things that bind to molecular oxygen, that kind of stuff. Okay? Cool? All right, so that's it for today.